A uniform solid circular disk of mass m is on a flat frictionless horizontal table. The center of mass of the disk is at rest and the disk is spinning with an angular frequency that is denoted by omega naught. A stone modeled as a point object, also of mass m, is placed on the edge of the disk with zero initial velocity relative to the table. A rim built into the disk constrains the stone to slide with friction along the disk's edge. After the stone stops sliding with respect to the disk, what is the angular speed of the disk and stone together? So we can use momentum conservation to solve this, or angular momentum conservation. So we know that the angular momentum before must be equal to the angular momentum after the interaction. And the angular momentum is given by the moment of inertia times the angular velocity. And so this says that the initial moment of inertia times the initial angular velocity must be equal to the final moment of inertia times the final angular velocity. So, I think we should probably draw a little diagram of how this might be working. So let's say that this is the y direction. Oops, let me draw a better line. And this is the x direction. So we're going to have a disk something like this. This is not a very good circle, but it's like a general idea of what it should look like. And suppose that it's centered around this, even though it doesn't look like it. Suppose it's centered around this. And we're going to have a radius r. So let's call the radius r. So the moment of inertia of a disk is given by 1/2 of the mass of the disk times the radius of the disk squared. So that's going to be our initial moment of inertia, since it's just the moment of inertia of the rotating disk. So we can ignore the stone for the initial one, but we need to solve for the final moment of inertia now. So now one thing to note is that once you put the stone on, the center of mass is going to move. So once this stone gets placed on, because it's quite massive compared to the disk, your center of mass is going to move. So the new center of mass can be determined by summing the masses, which the mass of the disk is just m, and its distance. And since we centered the center of mass of the disk on the origin of our grid here, that's just going to be 0. And the mass of the stone is the same as the mass of the disk, but its distance is going to be the radius. So it's the stone is going to have a mass of m. It is going to be a distance r away from the origin here. And now we have to divide it by the total mass, since this is the mass-weighted average. And so it is simply the sum of the two masses. And since they have the same mass, it's simply 2 times the disk mass or the stone mass. So if we evaluate this, the masses all cancel. This whole term cancels out too. So we're left with r over 2. So the new center of mass is going to be r over 2, or half the radius of the disk. So I can erase that now. So now we need to calculate the new moment of inertia of the disk, since the center of mass changed it here. So it's now going to be rotating around this point and not its center. So we can use the parallel axis theorem to find the new moment of inertia of the disk. So the parallel axis theorem says that for a point like parallel to the main, to the center of mass, the new moment of inertia is going to be the moment of inertia of the center of mass plus the mass times the distance to the center of mass. So the distance to the original center of mass. So in our case, let's calculate the new moment of inertia of the disk. So that's going to be equal to the initial moment of inertia, or the moment of inertia if it was rotating around the center of mass, which would be 1/2 mr squared plus the mass times the distance to the original center of mass, which is given by r/2 squared, and we're going to square that. So this becomes 1/2 mr squared plus this becomes 1/4 mr squared. So we can simplify this to give us 3/4 mr squared. And that is the moment of inertia of the disk after the stone has been placed. And we actually now need to calculate the moment of inertia of the stone as well. So the moment of inertia of the stone is simply its mass times its distance to the center to the rotation axis squared. So in this case, it's half the radius away from the rotation, from the new center of mass. So its moment of inertia is simply going to be 1/4 mr squared. 1/4 mr squared. And now to find the total moment of inertia, or in this case, the moment of inertia after the interaction, we just have to sum the moment of inertia of the disk and the moment of inertia of the stone. So this is going to be 3/4 mr squared plus 1/4 mr squared. And now this gives us a nice total of mr squared. So the final moment of inertia is simply going to be mr squared. Final moment of inertia equals mr squared. So I'm just going to erase all of this. So now the question is asking us for the angular velocity of the stone and disk together. So basically the final angular velocity after this interaction. So we can rearrange the equation to get that the final angular velocity is equal to the initial moment of inertia times the initial angular velocity divided by the final moment of inertia. So now we have everything, so we can substitute everything in. The initial moment of inertia is 1/2 mr squared, and of course we have the angular velocity, initial angular velocity, and we're going to divide it by the final moment of inertia, which is simply just mr squared. And so these two cancel. You're left with the final angular velocity is equal to 1/2 of the initial angular velocity, or the initial angular velocity divided by 2. And that is how you would solve this problem here.